Welcome back. I'm Muggsy, and today I'm going to explain the mole. The mole is a unit we use a lot in chemistry, and it can be very confusing at first, but it doesn't have to be. I think if we learn it correctly, it'll make a lot of sense and we'll be able to use it successfully. The important thing to know about the mole is that it's a counting unit. There are lots of units, like grams that measure mass, seconds that measure time, kelvins that measure temperature, that measure a specific thing. But there's also a bunch of other units that are just used to tell you how much of something there is. We call these counting units because they're just telling you the count of that thing. And I'm sure you know a bunch of these already. For instance, if I told you I had a pair of socks, you would know that that means 2. Or if I told you I had a dozen donuts, you would know that that means 12. We're not going to mess around with baker's dozen or any of that weird stuff. There's some weirder ones. So for instance, if I told you it happened a score of years ago, that means 20. That's kind of a strange one. And if I told you that something happened 100 years ago, or that I rode my bike for 100 miles, you would know that that's a century, which tells you 100. Cent, of course, meaning 100. Okay, so these are all counting units. They're not specific to any given thing. I could have a pair of socks. I could have a pair of eggs. I could have a pair of people. They're just telling you the number. Now, the mole is just another counting unit. The issue is that instead of being 2 or 12 or 20 or 100, a mole is this many. This many, a giant number. Now, as you might have seen from my scientific notation video, or just from knowing science in general, you'll know that we don't like to work with giant numbers like this. So in scientific notation, a mole is 6.022 times 10 to the 23rd of something. It doesn't really matter what that thing is. Again, it could be socks, it could be eggs. Usually we use it to refer to atoms or molecules. Now this huge number, 6.022 times 10 to the 23rd, is called Avogadro's number. It's named after the scientist that came up with the concept. And the reason we use such a big number is because atoms are so incredibly small. Let me explain. Let's think about making water. We want to take hydrogen, and we want to take oxygen. We basically want to stick them together to make H2O. Now we're going to need 2 hydrogens for that every 1 oxygen. And in reality, it's going to be a little bit more complicated because oxygen doesn't exist all by itself in this monoatomic state. It would be O2 and we'd have to balance this and all that. But let's just use this simplified equation for now to talk about the concept of a mole. Okay, now imagine we were trying to synthesize water in the lab, which you could do. You could combust hydrogen in the presence of oxygen and you'll get water. They will combine to make water. But we can't just take 2 hydrogen atoms, just pick them up and stick them together with 1 oxygen atom that we pick up and make water. Because atoms are so incredibly tiny. Again, they're much, much smaller than cells. They're much, much smaller than organelles. They're even smaller than molecules. Molecules are made of atoms. So they're really incredibly tiny. You know, there's just a massive number of atoms in a postage stamp or in a little gram of a substance. And so because we can't take 1 atom and add it to 1 atom of something else, we have to work with bigger quantities. We live in the world where we have to scoop things and pour things. And so we want to work with quantities like grams or milliliters or things like that. So we can't take 2 hydrogen atoms, which are so incredibly tiny. There's no machine we can use to even collect 2 atoms. and combine it with one oxygen atom to make one water. That's just totally impossible. But let's think bigger from there. What if we had two pairs of hydrogen atoms and a pair of oxygens? We can make a pair of water molecules. Well, it's a little bit bigger, but that's still much too small. What about a dozen? Well, we're getting bigger, but it's still much too small. If we had a mole, well, that's such a big number. Remember, it's 6.022 times 10 to the 23rd atoms in this case, but it could be anything. That we can actually have enough to work with. For instance, if we had a mole of hydrogen, that would have a mass of 1.01 grams. We call this the molar mass. And if we had a mole of oxygen, that would have a mass of about 16 grams. And finally, these numbers are big enough that, again, we don't need to grab individual atoms, which is impossible. We can actually take a decent quantity, 1 gram of hydrogen and 16 grams of oxygen, and combine them to make our water. In this case, about 17 grams of water. But now, where did these numbers come from? Did I just pull them out of nowhere? Well, no. I pulled them out of the same place I pull so many things out in chemistry, and that's the periodic table of elements. If you look at the periodic table, you see that hydrogen has an atomic mass of 1.01. Likewise, oxygen has an atomic mass of 16. So notice that I wrote this down as molar mass. Molar mass is exactly the same as atomic mass. Now, why is hydrogen so much smaller than oxygen? Well, hydrogen just has 1 proton in the nucleus, whereas oxygen has 8 protons and 8 neutrons in the nucleus for a total of 16 big particles in the nucleus. Again, we can exclude electrons because they're so incredibly small. So every one oxygen atom is 16 times bigger than every one hydrogen atom, right? And so even though this is a mole and this is a mole, this one's much heavier. And a good way of thinking about that is with counting units, it doesn't tell you anything about the mass or the speed or the temperature or anything like that. Let's think of the example of mass. If I have a dozen quail eggs, they could probably sit here right in the palm of my hand. But if I had a dozen ostrich eggs, that would be huge, right? I would need a massive basket to hold them. They would weigh a whole lot. A dozen quail eggs, I don't know what that weighs. Let's say, I don't know, 30 grams or something like that, where a dozen quail eggs would be several kilograms. I don't know, maybe each egg is close to a kilogram itself. So let's say that's 10 kilograms. So absolutely massive versus pretty small, because it's the same number, 12 and 12, but because each individual quail egg is so small, it's a small mass. And because each individual ostrich egg is so big, it's a big mass. And it's the same here. A mole of hydrogen is a small number, 1 gram, and a mole of oxygen is a bigger number, 16 grams, because each oxygen atom is so much bigger than each hydrogen atom. And this is true of every element in the periodic table. The mass of 1 mole of that element is the same as its reported atomic mass in the periodic table. So for any element, let's say it's carbon, you could look it up in the periodic table and see that an average mole of carbon atoms has a mass of 12 grams. Magnesium, look it up, average mole of magnesium atoms has a mass of 24.3 grams. Magnesium atoms are about twice as big as carbon atoms because they have about twice as many protons and neutrons in the nucleus, so it's a bigger mass. Now, why 24.3? Well, remember, we have to consider isotopes. And so different isotopes of magnesium might have different numbers of neutrons, and so it just averages out to 24.3, given the abundance of all magnesium atoms in the world around us. The last thing I want to do when talking about the mole is just kind of practice doing unit conversions with these counting units, including this new mole unit. But first, let's do a much easier example. So let's say I have, let's stick with eggs, 36 eggs. And we want to know how many dozens that is. You might have done a problem like this many years ago in elementary school. It's not a very complicated problem, but it is a good chance for us to practice our unit conversions. So again, with my unit conversions, the first thing I always do is write down 36 eggs. Then I make a blank conversion factor. I put the unit I want to get rid of on bottom, and that's eggs. I put the unit that I want to go to on top of the conversion factor, and that's dozens. Then, this is the critically important part of this problem, I think about the relationship between these two things that makes sense. For every 1 dozen, there are 12 eggs. It should make sense as you speak it aloud as a sentence, and if you kind of flipped the numbers, you should be able to catch that by thinking of it. For instance, if I put the 12 on top and the 1 on bottom, I would say for every 12 dozens, there's 1 egg. No, that doesn't make sense. For every 1 dozen, there's 12 eggs. Okay, and so now I just do the math. 36 times 1 is 36. 36 divided by 12 is 3. Cancel the units. Eggs divided by eggs is nothing, and we end up with dozens on top. 3 dozen. Okay, hopefully that was painfully easy for you, because now we're just going to do a more complicated version. It's basically the same thing. We're just going to use much bigger numbers, because again, a mole is a really huge number because atoms are so incredibly small. In fact, if you took all the sand on Earth, that would be less than a mole of sand, because an atom is so much smaller than each particle of sand. I don't know how many atoms are in a particle of sand, but it's a lot. I'm going to guess billions, maybe? A massive number of atoms in a tiny little particle of sand. Let's do another conversion problem. This time, let's say I have 5.419 repeating. We'll call it 99 times 10 to the 24th. Let's say hydrogen atoms. And we want to know how many moles that is. Well, again, this is a unit conversion problem using a counting unit. It's no different from that last problem we did with, was it dozens? Yeah, with dozens. It's just the number's bigger this time. So we're going to set it up exactly the same way. So we're going to start by writing out our starting value, 5.4199 times 10 to the 24th atoms. And then we're going to multiply that by our conversion factor. Now, before I put any numbers in here, I'm going to do the words. Atoms I want to get rid of, so it goes on bottom. Moles is what I'm trying to get, so that's going to go on top. And then here, I'm just going to use Avogadro's number. Now, depending on your class, you may be asked to memorize Avogadro's number. Often you'll be given a reference sheet with Avogadro's number on it for tests and stuff, so you don't need to. That's up to your teacher. But I do have it memorized, obviously. And so for every 1 mole, that's 6.022 times 10 to the 23rd atoms. Okay. So now atoms is going to cancel with atoms, leaving moles. And now we just need to do the math. No different from that last problem. The only difference is these numbers are bigger, right? So 5.419 times 10 to the 24th times 1 is just 5.4199 times 10 to the 24th. And 5.4199 times 10 to the 24th divided by 6.022 times 10 to the 23rd is, I have no idea. Let's do the math. Okay. So one thing I might do is make first of all, you could just put this in a calculator, but let's try doing it without a calculator just to flex. So I'm going to call this 54.199 times 10 to the 23rd. Basically, I just wanted to make both of these exponents 23. So in order to make this exponent smaller, 24 becomes 23, I need to make my number bigger by 1. So I just moved that decimal place over once. So 5.4 became 54. Okay, times 10 to the 23rd divided by 6.022 times 10 to the 23rd. Well, these are exactly the same, so I can ignore them. I don't need to do anything with them. And it now just becomes 54.199 divided by 6.022. And I'm not sure exactly what that is, but it seems like it's roughly 54 divided by 6 is 9. So my answer is roughly 9 moles. And of course, you could put that in a calculator. Am I down here? Am I up here? You can put that in a calculator if you want to get the exact answer. I just wanted to use my scientific notation skills to get a good estimate as quickly as I can without using a calculator. Okay, so doing conversions between atoms and moles or molecules and moles. Remember, a mole isn't specific to an atom. It could be anything. You could have a mole of eggs, a mole of people, whatever. But in order to do those conversions, you would set it up like any other unit conversion. Please check out my unit conversion video if you're not really comfortable with this method. This method will take you far in life if you set up your unit conversions like this. And then for every element in the periodic table, the mass of 1 mole of that element is simply equal to the atomic mass. And we just call it the molar mass, but it's exactly the same. Yeah, I've got future videos on calculating molar mass and that kind of stuff. And I've got past videos that might help you on things like unit conversions, atoms, isotopes, all that kind of stuff. I wish you luck with the mole. I had a hard time learning it when I was a student, but I think having it explained to you like this will help a lot. It's just a counting unit, just like a dozen or a pair, but instead of a small number like 2 or 12, it's a huge number, 6.022 times 10 to the 23rd, which we call Avogadro's number. All right, I wish you luck. Take care.